Okay, Math 352, welcome back. We're up to lecture 17, and this lecture we're going to continue our discussion on positive definiteness and positive definite matrices, and we're going to look at a particular factorization of positive definite matrices called the Cholesky factorization. Now, this one is really practically useful, and it's what you always use if you're solving a system of linear equations that involve a positive definite matrix. Okay, so to warm up, we're going to just have a bit of a look at something. Remember, in the problems class, we said if a matrix A is positive definite, a couple of things to remember. We know that A is Hermitian, and one of the 4 tests we did was that naive Gaussian elimination, okay, that's just Gaussian elimination with no scalar multiples or row swaps, gives A equals LU. Okay, it gives us a usual LU decomposition, and all the pivots, i.e. all the diagonal entries of U, are greater than 0. Okay, so that's one of our properties of positive definite matrices. So what we're going to do is we're going to derive the Cholesky factorization from this. So what we're going to do is we're going to say, let A equal LU. Okay, fair enough. And then we'll say, define a diagonal matrix D, such that its ith entry squared is equal to ui. Okay, then our factorization becomes A equals L D squared. Okay, so D is just that diagonal matrix. Now, if we're multiplying a matrix by a diagonal matrix, that basically scales. If I multiply D squared times a matrix here, that will scale each row of that matrix by the corresponding entry of D. So we'll have an upper triangular matrix here, which is basically U, where each row has been divided by UII. Okay, so R upper triangular. Okay, so what we want to do is we want to show okay, so what we got, we'll just have a look at the factorization again. We've got a unit lower triangular matrix times a D squared times a diagonal matrix times a unit upper triangular matrix. Remember, when I say unit for a triangular matrix, I just mean that there's ones along the main diagonal. If we can show that R is actually just the conjugate transpose of L, then that will give us our Cholesky factorization. Okay, so the Cholesky factorization, which we'll come to in a minute, is basically lower triangular matrix times its transpose is equal to A, or conjugate transpose for complex ones. Okay, so how are we going to do this? Well, first off, one way of doing this, we're going to say let dr equal m dl star for some invertible matrix okay, note we can do this as m is just equal to dr dl star inverse, and d and l star are both invertible. Okay, so what we're saying is, okay, if we wanted to show that r equals l star, great. So if we can show that m is the identity, okay, that's equivalent to showing that R equals L star. If M is I, then we've got dr equals dl star, and we'll have the relationship that we want. Okay, so let's see what we can say about M. Okay, so we know that A equals A star, okay, because our matrix, that's where we started with. So if we plug our various pieces in here, L d squared R therefore equals R star d squared L star. And now I'll plug in my expression here. If I plug in M dl star, dr equals M dl star, I get, let's see, L d M dl star is equal to L d M star. Just taking the conjugate transpose of this. L d M star d L star. Okay. So all I'm doing is plugging in my definition of this matrix M here in a roundabout kind of way. And so we know this matrix M exists. Here's a condition on it. And we know that L and D are invertible. So if we just multiply the left by LD inverse and the right by DL star inverse, we get M equals M star. Okay, what else do we know about M? Well, let's see. Back at our definition, here we have upper triangular. Here, what do we have? We have upper triangular. So M itself must be upper triangular. M is also upper triangular. So this implies that M is in fact diagonal. Okay, and there's one other thing we can note. R and L star are both unit upper triangular matrices. dr and dl star are both upper triangular matrices, and they have the same diagonal entries because they're multiplying unit upper triangular matrices. So finally, dr and dl star have the same diagonal entries. Let me scroll down a bit. So that implies from our above relationship here that M is not only diagonal, but M is the identity. Okay, so hence A is equal to L d squared L star. Okay, and that is pretty close to being the Cholesky factorization of a matrix A. Okay, so let's just define this a bit more formally now. So, Cholesky factorization. Cholesky, so we've shown that our matrix A is equal to L d squared L star with dii greater than 0 for all I. and L unit lower triangular. Okay, the Cholesky factorization of A where we'll just note A positive definite. The Cholesky factorization of A is given by A, I'll call it L hat transpose, where L hat here is equal to L times D. Okay, so the Cholesky factorization of a matrix is basically breaking it up into the product of a triangular matrix with its transpose. And obviously this one here is for our real case. Okay, so real positive definite symmetric matrix A. Same thing applies for complex, but you end up using these a lot more for real matrices. Okay, we can also define a related one, the modified Cholesky decomposition or factorization. Let's just avoids. Okay, the one drawback of doing this one is you've got to take a square root. Okay, so that dii is equal to the square root of uii. We don't really want to be taking square roots if we can avoid it. So the modified Cholesky factorization avoids this. By basically just not incorporating the matrix D into the vectors. So you get A equals L D hat L transpose, where D hat is just that D squared we had before. Okay, it's often more convenient to express your factorization this way. You don't have to take any square roots. You just leave the D squareds as a separate diagonal matrix. Okay, so that's basically, we've done most of the work. So let's do an example. Okay, so for example, we'll take a matrix A, and that will be given by 4, negative 4, 8, negative 4, 6, negative 2, 8, negative 2, and 35. Okay, now we haven't actually tested to see whether this thing is positive definite yet, but as I'll talk about soon, actually going about trying to compute a Cholesky factorization is as good a way as any. In fact, it's probably the best way of checking whether a matrix is positive definite or not. Because if it's not, then at some point the process of computing this factorization will just break down on you, and there's your proof. So we're going to do naive Gaussian elimination on this. So using naive Gaussian elimination, so we just do our row operations the way we normally would. So first off, we'll do two row operations here. We'll go row 2 goes to row 2 plus row 1, and row 3 goes to row 3 minus 2r1. Okay, let's just write that again, it's a mess. Row 3 goes to row 3 minus 2 row 1. Okay, so we get the top row. So we resist the temptation to multiply this by a scalar, because that would be bad. That gives us a 0. We just add this one on, that gives us a 2. That gives us a 6. Now we're taking twice the row off, so we get a 0 there. We're taking twice negative 4 off, so we get a positive 6. And we're taking away 16, so we get 19 here. Okay, next step. Well, we've got to clear a 0 into there as well, so we'll do row 3 goes to row 3 minus 3 row 2. Okay, kind of fun to do Gaussian elimination every now and then. That'll give us a 0 there, and that will give us a 1 in that remaining spot. Okay, so this here is our U. Now we know that U, so we also know that D squared is the matrix of the diagonal entries. And R is basically we take our U and we divide each row by the corresponding entry in D squared. So we'll get a 1, a -1, and a 2. We'll get a 0, a 1, and a 3. And we'll get a 0, a 0, and a 1. So that's our R, which is also our L star. Or in this case, because we're working with the real matrix, it's our L transpose. Okay, so A is which also equals D hat. L D hat L transpose. Okay, you can test that for yourself in MATLAB or something. And what else? Ah, yes. If we want to express our Cholesky factorization in the original form, we get L hat equals D L transpose. Oh, it's L hat transpose. L hat equals LD, sorry. Which in this case, we're just going to take the square roots of these entries. So that will give us the matrix 2, 0, 0. So I'm taking the transpose here. -2, √2, and 0. And 4, 3 √2, and 1. Okay, so how do we know that this worked? Well, the first thing, our matrix is, okay, the first thing we would have had to verify, our matrix is symmetric, and it's got real entries. Okay, so we're relying on the fact that it's symmetric here. That is something you need to check beforehand. We do our naive Gauss elimination, and we notice that we end up with three positive pivots. Okay, because those pivots are positive, we know we've got a positive definite matrix, and our Cholesky factorization method that we just did before is going to work. So we can just confidently at that point in time write down the Cholesky factors because we know that our matrix is positive definite. We found that when we did our Gaussian elimination. Okay, so that's one way of computing a Cholesky factorization. There is in fact another method which does essentially the same thing but looks a bit different, and this is called the modified Cholesky factorization. So the Cholesky and modified Cholesky, which we'll talk about in a moment, factorizations require in practice about half the work. Okay, so they require about half the work of the LU factorization. Okay, it's not obvious from what we just did then, but I'll show you a way of expressing this method that will make that clearer. Okay, so essentially, with Cholesky, the fact that once you've got one of the triangular factors, you've got the other one. So the fact that U equals DLT and the elements of DL transpose occur anyway when finding L, that means that U is basically free. You get it for free. Okay, so what I'm going to do is I'm going to do a big example here, just to sort of make this clear without giving you the algorithm in any kind of formal sense. So let's see what happens. So what I'm going to do is I'm going to write down a general 4x4 matrix A. We're going to assume it's symmetric, but I will write all the entries in full anyway. So A11, A12. Okay, you can maybe have a drink while I write these down. A21, A22, A23, A24, A31, A32, A33, A34, almost there with this one. And I'll write down its general LU factorization. So remember, it's always the L factor when we're taking an LU factorization is given by the product of a unit lower triangular matrix and an upper triangular matrix. And if our matrix is positive definite, then we know that these diagonal U's are positive. Okay, they're not zero, they're positive, definitely. Okay, so that means we've got this big factorization, and what I'm going to do is I'm going to show you sort of how the Cholesky factorization can be computed directly from this expression here. The LU can as well, and I'll show you the difference between the two. So let's just start writing down some expressions. I'm going to start here, and I'm going to work my way down the first column. So from our first equation gives us A11 is equal to first row, first column, A11 equals U11. And what I'm going to do is I'm going to write down the variable that we haven't yet seen in a different color. Okay, so our first equation allows us to solve for U11 directly. That also equals D1 if we're computing the D factors too. A21 is equal to L21 U11. Okay, that's just going across here and down there. Likewise, A31 equals L31 U11, and A32, so A41 equals L41 U11. Okay, so those first four equations allow us to compute U11, L21, L31, and L41. No problem. Okay, if we were doing regular LU decomposition of a general matrix, then we'd also have to do the following. A12, we then go across, so we've gone down here, and then we have to go across here. So we'll start writing down some expressions for these entries. So A12 equals, once again, it's going to be first row, 1, second column, U12. Okay, so now we're getting these entries here. A13 likewise equals U13, and A14 equals U14. Okay, so if we're doing our general LU, we go that way. That gives us these entries as well. So we've got 7 equations to work out 7 entries of our matrix. Okay, now let's go down there. So we've done that. Next step is to go down here. So A22 is equal to, let's just multiply this out without making too much of a mess. So second row, second column, L21, we already have L21, so we can write it in black. U12, we've got that from up there, so we can write that in black as well. Plus U22. So notice each time I'm writing down one of these expressions, I've only got one new variable, so I can always solve for it in terms of the other ones. A23 equals L31 U13. Is that right? L21 U13. Okay, and we have U13 already from over here, so we can write that one down in black as well. Plus L32. Do we have that yet? No. So what am I doing here? I'm writing down the wrong one. Sorry. I was wondering why this wasn't really working for me. We should be doing A32, not A23. Okay, so A32, sorry. Third row. L31, U12, plus L32, which is unknown, U22, which is known. Okay, so we're still satisfying this property that each time we get to a new equation, there's only one new variable, so we can solve for it in terms of the preceding ones. And finally, A42 is going to be equal to this one here, so L41, which we already know, times U12, which we already know, plus L42 times U22. Okay, so that's given us 3 new entries, and once again, if we're doing a general LU, we then go across these entries here. Okay, so let's just quickly write those ones down. So we need to do A23, which is the one I was trying to do before. A23 gives us L21 U13 plus U23. So that's a new one. And A24 is equal to L21 U14 plus U24. Okay, at this point in time we're almost there. That's given us some more entries. We've got a couple more things to do. So we're just going to zip down this column here. I'll just quickly write these down now because you should be beginning to get the idea. And, well, we can sort of refer to part of the matrix. A33 equals L31. We've already got that. U13, already got that too. Plus L32, already have that. U23, already have that. Plus U33, we don't have that. That's the new one we can get. Going down to A43, we get L31. Is that right? L31. I'm getting myself confused. A43, that one there, row 4, so L41 U13 plus L42 U23 plus L43 U33 plus, what's missing? L43 was our new one. That's all. And finally, if we're doing a general LU, we need to go this way as well. So we'd get A34, third row, fourth column gives us L31, U14, we have those, plus L32, U24, we have that too, plus L3, no, plus U34. Okay, we've got one last one to do, and then we're done. So A44, last row, last column, L41, U14, plus L42, U24, plus, scroll so I can write it better, L43, U34, we've got all of these things, plus U44. Okay, so that's a really explicit way of computing an LU factorization of a matrix. Now, the kind of very long-winded point I'm getting to here is that if we have a positive definite matrix, or even a symmetric matrix, then these ones here, but we know U12 is just good. Well, we know that D1 1 squared U12 is equal to L21. Okay, so if we've got a symmetric matrix like this, we actually already know this entry, so we don't need to compute it. Likewise, we already know this one. We already know this one because we can get these from our left-hand sides, from the lower triangular factors. So basically, we don't need to do any of this. For a symmetric matrix. Okay, because we can work out these extra entries from entries that we've already found on the left-hand side there. So kind of asymptotically, as you get to bigger and bigger matrices, the amount of work involved in these two sides is about the same. So in that sense, the amount of work required to do a Cholesky factorization is about half of doing a general LU. Okay, now I'm talking that this sort of works for a general symmetric matrix. However, it has numerical stability issues if it's not positive definite. So let's just make a quick note about that. If A, so obviously I haven't given you that algorithm in a formal sense. If you want to code it up, then you're more than welcome to have a play with that. It's a good idea. But I've just sort of touched on it to give you an idea. So if A is positive definite, then both types, okay, the Gaussian elimination version and the more explicit one we just did then, both types of Cholesky factorization are numerically stable. Okay, for non-positive definite matrices, but symmetric, the LDL transpose factorization sometimes exists, but not always. Okay, with some negative DIIs, but is numerically unstable. Okay, so the nice thing is if your matrix is positive definite, then your Cholesky factorization that you will have computed will have been done in a numerically stable way. So for example, just quickly, A equals 0, 1, 1, 0 has no LDL transpose factors. Okay, you can try and find them if you want. You will not succeed. Okay, A, I'll give you another one. Okay, so I've got a matrix with small main diagonal entries and one on the off diagonal. If you work out your factorization there, you get 1, 0, 1 over epsilon 1 times epsilon, epsilon minus 1 over epsilon, 0, 0, 1, 1 over epsilon. You can check this for yourself, 0, 1. If epsilon is small, then 1 over epsilon is large, and some L and D elements are much greater in magnitude than A elements. Okay, so in the literature you call that it's got a large growth factor. Okay, so this is numerically unstable because of cancellation and round off. So kind of refer to our earlier lectures for this stuff. Okay. Finally, let's give an example of a matrix that does have an okay set of LDLT factorization. So 1, 0, 0, negative 1 has L equals I and D equals, well, itself, 1, 0, 0, negative 1, which is okay. Okay, so some matrices that are not positive definite have this factorization that works, but it's also possible that the factorization will be numerically unstable, like this one here. Okay, so just to sort of round off this bit, we've got a method for computing a factorization of positive definite matrices. What I'm going to give you is kind of a good way of a good procedure to go about checking whether a matrix is positive definite or not. So I've got a few different properties of these things. So if you want to find out whether a matrix, if you're given a matrix, you want to find out whether it's positive definite or not, here's kind of a procedure you could follow. So quick tests. 1. Is it symmetric or Hermitian? Okay, if that fails, it's not positive definite. Okay, that's an easy one to do, doesn't really require much work. 2. All the diagonal entries of A need to be positive. Okay, so I'll get you to try that one out in a tutorial. If that fails, it's not positive definite. Number 3, the largest element of A in modulus is on the main diagonal. Fail, not positive definite. Okay, these are all things you can pretty much inspect visually. 4, okay, who remembers Gersh-Göran's circle theorem? Okay, well, let's just quickly run through that one. So, remember Gersh-Göran's theorem. Basically gives us bounds on where the eigenvalues of a matrix can lie. Remember, for a positive definite matrix, all the eigenvalues should be positive. So, each eigenvalue lambda of B, which is an m by m matrix, satisfies at least one of the following. Okay, inequalities. Lambda minus diagonal element modulus, okay, so the distance of from lambda in the complex plane from the diagonal element BII is less than or equal to the sum from j equals 1 to m, not including I, of the absolute values of Bij, which you may as well call Ri. Okay, so what does that mean? That means each lambda lies in the union of the disks of radius I and center Bi. Okay, so that's the first part of it. The second part deals with the case where some of the disks are disjoint from other ones. If the union of k disks is disjoint from the remaining ones, then k eigenvalues lie in that union. Okay, so basically you draw disks around the various diagonal entries of your matrix, and you see that tells you where the eigenvalues lie. Okay, so if your matrix had, let's just do an example. Let's do it here. 4, 2, 1, 0, 1, 0, negative 10. No, let's not do that. Let's make one that is positive definite. 0, 1, 0. Then basically, your first one is centered at 4 and has a radius of the sum of the off-diagonal entries, which is just 1. Second one is centered at 2. Actually, let's make this number 1 and 1. And it also has a radius of 1. And the third one is centered at 1 and has a radius of the sum of these entries, which is 2. So that looks like... Okay, so basically this says that all of the eigenvalues of this matrix lie somewhere within the interiors or boundary of these disks. Okay, and if this entry had been slightly smaller, like 0.9, then these two would be separate by a little bit, and the second part of the theorem tells us that 2 of the eigenvalues would be in this section and 1 of them would be in there. Okay, so let me just quickly check how much time I've got. A little bit more, that's good. So let's just have a quick, we can probably quickly prove some of that. Yep, I'll prove one more thing and then we'll probably be about done there. So we can prove this. Proof. Let's prove part A. We know that if x is an eigenvector with an associated eigenvalue lambda, we know that bx equals lambda x. Okay, and if you're looking at just one particular component, this means that the sum from j equals 1 to m of b, I'm just looking at the ith component, xj equals lambda I xi. Alright, so this means, if we just take this expression and rearrange it slightly, lambda minus, I'm using capital B, I should be using a small b, sorry, lambda minus bij bii xi equals, so I'm just basically plucking out the bii entry from here, so the same sum, except that I've taken the I entry out and put it on the other side, of bij xj. Okay, for I equals 1 to n. Therefore, if I take the absolute values of both sides and divide by the absolute value of xi, is less than or equal to bij xj and xi. Okay, so that's good. So that's basically using a triangle inequality. So pick an I such that xi is greater than or equal to xj for j equals 1 to n. So I'm just going to pluck out the biggest one and choose that to be my I. This means that this expression here, well, we can get an upper bound on the right hand side by turning all these into ones. Less than or equal to the sum j is not equal to I of absolute value of bij. Okay, and that is our Gershgorin's circle theorem expression as required. So why does that work again? Well, basically, to get from this expression to this one, we multiply each term by a quantity that's less than 1, or less than or equal to 1. So this one is definitely an upper bound on this, and therefore we've proved what we wanted to prove. Okay, so let's just look at one more application. It's a nice quick one, and it's a good application of positive definite matrices, which we'll come back to again. So minimizing a complex quadratic. So we're going to look at a complex quadratic form. Q of z is equal to z star az plus a star z plus z star a, where a is positive definite. Okay, the reason I'm adding these two complex conjugate things together here is so that I actually get a real number out. Now if a is positive definite, this means that A inverse exists. So we can do the following. If we look at this expression here, which is similar but not quite the same, z plus A inverse A star A z plus A inverse A. Expand this thing out, we get z star az plus a star z plus z star a plus a star A inverse A. Okay, now this is just vector star times positive definite matrix times vector, okay, which is greater than 0. So this expression here is minimized. Well, the smallest you can make it is by start again. Remember that if A is positive definite, then this expression here is essentially W star A W. Okay, and we know that this expression is positive for any choice of non-zero vector W. So the smallest we could make this expression is 0, and that's if we choose z is equal to negative A inverse A, which makes this vector 0. So because A is PD, Q is minimized by choosing Z equals negative A inverse A. Okay, because this expression here is the same as this one, except for a constant. Okay, so minimizing this expression is the same as minimizing Q, except the actual value you get is going to be different. And has minimum value well, the minimum value of this one is going to be 0, and to get from this expression to this expression up here, we just take away A star A inverse A. Minimum value negative A star A inverse A. Okay, now almost finished. One more thing to do. Sorry, I thought I was finished, but actually realized I had one more thing I had to tell you about. So this one will only take a second. Another useful piece of information that I'm just going to state really quickly. It's called Sylvester's law of inertia. And if A and B are Hermitian, and we let A is equal to S star B S for some non-singular S. Okay, so if we've got an S such that that's true, then A and B have the same number each, of positive, negative, and 0 eigenvalues. Okay, so this means that signs, not values, are preserved under these similarity transformations. Okay, so that's just another little thing that can occasionally be useful. If you know that a matrix A is related to some other matrix B, which you know things about, by a similarity transformation like this one here, then basically you know that the eigenvalues are related and that the signs are not going to change. So if A is positive definite, which means it's got all positive eigenvalues, then B must be as well, because we're not going to be able to get any different negative or 0 ones. Okay, and just to complete the lecture, it's getting a bit comical now because I keep saying that. Just remember what I was doing before. I gave you 4 tests for positive definiteness. Once again, if this one fails, i.e. if we get like a circle out here, that means we've got a negative eigenvalue, so fail, not positive definite. If all of these fail, sorry, if 1 to 4 succeed, okay, so if our quick tests don't rule out A being positive definite, then compute a Cholesky. Okay, so if you do these 4 tests and they don't rule out your matrix being positive definite, the next thing to do to test is to compute a Cholesky factorization. And if that works, then you know that your matrix is positive definite. So like I said, this is the way in practice that you test matrices for positive definiteness. Because if they're not positive definite, you usually find out about it pretty quickly in your process. You get a negative diagonal of some sort. Okay, so that's basically what you do. I promise I'm actually finished this time. So that's enough for this lecture. I'll see you all back next time I see you.